In the last lecture, we discussed how a transformer works. Now today, we'll try to design a transformer. For designing the transformer, what you know, we'll have to calculate how many number of turns will be there in the primary, how many number of turns will be there in the secondary, how much current will be flowing through the transformer. So let us derive some small formula which will help us to design a transformer which we want. So just to have a quick recapitulation, if we apply a voltage here, this is V1 voltage if I am applying, then this side is called primary and this side where load is connected is called the secondary. So as soon as you applying this voltage, a current will be flowing through this. This current, I1 current, will be producing a magnetic flux which will be traveling through this core of this transformer. So this flux is phi, flux phi. So now we know that we apply AC voltage. AC voltage is a sinusoidal voltage which will produce a sinusoidal current, and that will in turn produce a sinusoidal flux. So the flux phi is phi m, we can say sine omega t, where omega is the circular frequency. We call this, it is called circular frequency. Omega is actually 2 pi f. F is the frequency of the supply. In our India, it is generally 50 hertz. So this frequency of supply, if we apply, then we will getting a sinusoidal flux. Now, as soon as flux is generated, there will be a self-induced EMF here. That EMF, let us call it E1, is the EMF which is produced in the primary coil, self-induced EMF, which will be counterbalancing this V1. Now, how much is the self-induced EMF E1? That by Faraday's law, we know that will be number of turns of the primary into the rate of change of flux. That means it will be minus n d phi dt. So n primary number of turns, if we say this is n1, then it will be n1 d phi dt. Now this so it will be minus n1 d phi dt. If I differentiate this phi with reference to t, then I am getting omega phi m cosine omega t. It will be cosine omega t. So this n1 omega phi m is the amplitude of this induced EMF E1. So if I want the RMS value of the induced EMF, generally changing value of any AC quantity is represented by a small letter and RMS value by a capital letter. E1 will be equal to minus n1 omega phi m divided by root 2, because amplitude divided by root 2 for a sinusoidal signal, it will give its RMS value. So if I make it n1 omega, I can write 2 pi f into phi m by root 2. So I am getting E1 is equal to, if I do it, it will be 4.44 n1 f phi m. This is a very, very famous formula. This is a very, very famous formula. Wherever there will be induced EMF, that induced EMF will be guided by this formula. E1 is equal to 4.44 n1 f phi m. That will be the RMS value of the induced EMF. Now we know the same flux will induce an EMF E2 here. Here another EMF E2 will be induced, and that induced EMF will drive current through this L load which we have connected. Load can be anything. It can be fan, it can be pump, it can be any motor. So we can write that similarly. We can write E2 is equal to 4.44. Now number of turns in the secondary is N2 F into phi. So here number of turns is N2. So I am finding the induced EMF equation of these two. Now if I divide E1 by E2, if I divide E1 by E2, what I am getting? I am getting N1 by N2. So this is another guiding formula of transformer, that is voltage, induced voltage E1 by E2 will be equal to always N1 by N2. And as E1 and E2, E1 is directly proportional to V1, V2 will be directly proportional to V2, so I can write here it is almost equal to V1 by V2. So this ratio will always be maintained in the transformer. So now we can say, what about the current? We found that this current flowing through the transformer will be guided by the principle that input power and output power remain constant. So what is the input power? Input power is E1 into I1. What is the output power? Output power is E2 into I2. So this should be equal. So then I can say E1 by E2 is equal to I2 by I1. So I can write here in this famous formula, E1 by E2 is equal to N1 by N2 is equal to I1, I2 by I1. So this is the complete guiding formula for the transformer. These are the formula for the induced EMF. Now you notice what is the induced EMF per turn. Number of turns is N1. So per turn how many voltage will be induced? Let us see, E1 by N1 is equal to 4.44 into F phi m. Phi m is the amplitude of the flux. So that is equal to, this is equal to E2 by N2. From this formula you can find E2 by N2 is equal to same 4.44 F into phi m. So what is this? What does it mean? It means that per turn voltage across the transformer, both at the primary and secondary, both are same. That means per turn voltage in the primary and per turn voltage in the secondary will be same. Only it will depend on number of turns, how much voltage we are getting here. So where number of turns is more, voltage will be higher. Where number of turns are less, voltage will be lower. The side where voltage is higher is called HV side, that means high voltage side, and some people call it HT side, that means high tension side. Voltage is referred as a tension. So, and the side where voltage is low is called LV side or LT side, that means low tension side. So in the two sides of the transformer, we are now getting three terminology. Where the side where voltage is applied is called primary, the side where load is applied is called secondary. The side where voltage is high is called HV side or HT side. The voltage where it is lower, then it will be called LV side or LT side. Now with this formula, in the next lecture, we will find out how we design actual transformer.